What's up everyone, Jason Turley here, back with another video. Today we'll be going over a set of challenges from ROP Emporium, which is an online website that has different CTF style challenges for exploiting binaries using a technique called return-oriented programming, or ROP for short. So if that's anything that interests you, this would be a good series. To get started, I recommend reading the Beginner's Guide, which has a bunch of introductory tips and information and tidbits on how to get started, different tools to use. I'll be showcasing some of them, some general advice, and so on and so forth. So if you are going to do these challenges, I would recommend reading through this page in its entirety. But let's dive in with the first challenge, ret2win. If we click on it, we can see the description reads, locate a method that you want to call within the binary, call it by overriding a saved return address on the stack, and you do have your pick of 4 different architectures that you can choose to download the binary. You have x86 64, which is what we'll be using. You have x86, so 32-bit binaries. You have ARM, and you have MIPS. And while you'll be using a buffer overflow exploit for all 4 of these binaries, things like the registers and whatnot, the registers that you want to set up on the stack will be different for each one. Even though you're doing a buffer overflow, the exact steps of the exploit will change a tiny bit depending on the architecture. So I'll be going over the x64 bit, the 64 architecture in these challenges. So without further ado, let's right click and copy the link, switch over to our terminal where I already have a working directory for YouTube ROP Emporium created. Let me make a directory. Actually, let me just download with wget our challenge file. We see the zip file successfully downloaded. Now let's unzip that. And specify the output directory with tech D and then ret2win. Now if I do an ls, I have the zip file, and I also have a new directory created that has the flag as well as a challenge binary already created. I no longer need that zip file, so I'm going to delete it and then change directories to our ret2win. Now these challenges are a little different. The flag is already given to you, and our goal is to run this binary and exploit it with a buffer overflow attack to get it to print out the flag. And that will change throughout the course of the challenges as they get progressively more difficult. So if I run the file command on ret2win, we see it's an ELF file, executable and linkable format for the Linux operating system. If you are on Windows, this would be a PE, a portable executable. It's 64-bit executable. It is dynamically linked, meaning any libraries it needs are not contained within the binary. Those are located somewhere else on the file system, and it will reach out and grab those as it needs it. We see the interpreter used, and then we see here it is not stripped, which is nice because we are going to be debugging and disassembling this. So it will have useful information like symbols names and function names and whatnot. So if I run the challenge, it prints out ret2win by ROP Emporium, specifying it's the x86 64-bit version. And if we read this message here, it tells us it will attempt to fit up to 56 bytes of user input into 32 bytes of stack buffer. So what could possibly go wrong? You there may have your input please, and don't worry about no bytes while using read. So if I type in whatever, it prints out thank you and exit. So let's see if we can fuzz this program and get it to crash at all. I'll do Python cprint. Let's just throw 100 A's at this thing. There we go. And let's pipe that into ret2win. And we see we do get a segmentation fault. Let's see if I can do dmessage tail. And right here, right at the bottom, you guys can't see that, dmessage tech t tail 1, we see a general protection fault was created, and we see the address of the instruction pointer and the address of the stack pointer. Now, if this were a 32-bit binary for the x86 architecture, our instruction pointer would be overwritten with A's, but on 64-bit architectures, it is a bit different. You can still overwrite the return address of the stack buffer. However, it needs to be something called a canonical address. It can't just be A's or B's or random junk. It has to be an actual valid address, something like this. So if we wanted to, we could keep characterizing the binary and seeing what's up with it with something like a robin2 with tac I that will print out all the different, ways and features this binary was compiled with. So we do see again a 64-bit if we weren't sure before. And here we see NX true, so non-executable, meaning we can't upload our shell code just directly to the stack because you can't execute code from the stack. Alternatively, we could have used checksec and then the name of our binary. Checksec ret2win, and we see the same thing. NX is enabled, so no stack canaries are found, which is good, and it's not a position independent executable, so ASLR is turned off. We could look at the strings of this binary, see if there's any function names or anything like that that could help us, and we don't really see anything useful. Let me pipe this into less. And this is okay. We do see functions called memset and read. We see bincat flag.text. We do see some function names. We see something called pwnme, and we see something called ret2win. If I kill this, and instead of doing strings, I do robin2 tac z ret2win. A lot less output is printed to the screen, which is nice. And we do get a bit of context. So we do get the virtual address that these are loaded at, which is pretty handy. So with that out of the way, let's do GDB on ret2win. And I do have GEF installed, the GDB enhanced framework. So it does have nice syntax highlighting and other usability features that make this preferable for exploit development. So if I do dis for disassemble and hit tab twice, we can see some of the different functions that are being used and imported in this binary. Once again, we see ret2win, we see calls to system are here, and that is nice because we can call system with something like binsh or bincat flag.txt to print out our flag. So let's start by just disassembling main, which is the entry point of this function. We see two calls to put string here, which are very similar to printf. So let's grab these and do x/x to examine as a string. And we do see the beginning of that message that was printed when we first ran the executable. Do that for this one. Okay, so it seems like these are just the messages that are being printed to the screen. We do see a call to pwnme, so let's disassemble that. We see a call to memset, and we see the arguments being passed to the registers here. If this were x86, so 32-bit with a different stack frame, perhaps these arguments would just be pushed directly onto the stack, and then a call to memset would be made. However, in x64, since it does have more registers than x86, it utilizes those by just passing the function arguments inside of the registers on the CPU. So let's break this down a bit. So if I open the man page for memset, we see it takes 3 arguments, void s, an integer, and then a size. So what is this? So memset function fills the first n bytes of the memory area pointed to by s with a constant byte c, and then it returns a pointer to the memory area s. So essentially what memset does, you give it some type of buffer, a pointer, and you give it a value and you give it a size. So you're saying, take this value and write it to that pointer, to that memory address, n times. So typically we see memset as memset buff, some type of input buffer, 0, and then a size like 128. So if this buffer is allocated with 128 bytes in C, there's no guarantee that those will be 0 or blank by default. If you allocate a buffer of size 128, for example, it will have whatever contents are currently on the stack. So it's good practice to clear out your buffers using something like memset. So write 0 to your buffer 128 times, or whatever the size of your buffer is, right? Size of buff. So if we come here, so the 3 arguments being passed are OX20. And if we're not sure what that is, we can do printf %d with a new line and then OX20. And we see that's 32. So before, when we ran the challenge, it did tell us that our buffer is 32 bytes in size, right? So we are here, we're allocating a buffer of size 32 bytes on the stack, and we're writing 0 into that buffer 32 times. So essentially we're marking this buffer as clear, as null, and then we see more calls to print string or put S, whatever you want to call it. We don't need to do this for every single challenge, but it is kind of nice just to get an idea of what's going on. So all we've done so far is allocated a buffer, and then we're seeing the different messages being printed out. We're seeing all this getting printed out, and then it's hanging and it's waiting for our user input. And to read our user input, it's using the system call called read. So all the arguments, all the registers directly before this read system call, this is what we want to concern ourselves with. So we see OX32 is being subtracted from the base pointer. That's because our buffer is 32 bytes in length, and that is being stored in the register RAX. If we really wanted to, we could look at the system call for read. So man3 read. Let's just do man read. So read will take a file descriptor, a buffer, and a size. So if we come over here, EDI and RDI will store the first argument. So we see the value of 0 being passed. So read from file descriptor 0, which is standard input, which makes sense. That's where we're typing from. So read from user input, read into our buffer, and read OX38 bytes. Before, it already told us that was 32, but let's confirm OX38 is 56, right? So we're reading up to 56 bytes into a 32 byte buffer. So we can overflow the buffer and we can overflow the return address. So we can manually fuzz it by throwing a bunch of A's or B's, just some random junk, but it might be better to use something like cyclic, or in GEF, if you have that installed, you can just use the built-in pattern command. Let's pattern create 56 bytes of random stuff. Let's grab this, and now let's run the program. It prints out all that stuff that we saw before, all these messages, and when it asks for user input, if we paste in these characters that we got from pattern create and hit enter, a cool thing about GEF, after it runs your program, we can see here ret2win stopped. The reason is sig-seg-v, so the segmentation fault occurred. If we do scroll up, we can see here, we see the address of the instruction pointer, as well as a bunch of random junk. We see RSP has a bunch of A's in it. And if we scroll down, we see it prints out the contents of the stack, forgive me. So if we want to find the offset to get to the return address, you can do pattern search $RSP, and we see the pattern it found, and we see that 40 bytes. It takes 40 bytes to fill the buffer, which is 32 bytes. And then after the buffer is something called the base pointer, which is used to calculate our current stack frame. And if none of this makes sense, let's look up stack frame for x64. This is a good blog post from Eli Bendersky, stack frame layout in x64. And if we scroll down, we do see this image here. So for the current stack frame, right, we have our buffer, we have the base pointer, RBP, and then we have the return address listed after it. And we can see here the order of the arguments being passed onto the stack, with the first argument being passed to RDI, then RSI, then RDX, and so on and so forth. So if we go back to our terminal screen, we do see that it will take 40 bytes to fill the buffer, and then overwrite the base pointer, and then everything after that will be RIP. It will be the return address that RIP, the instruction pointer, the program counter, whatever you want to call it, points to. So we can control the program counter. We can change where the program returns execution to. So this is called ret2win because the stack is not executable. We can't just place our shellcode on the stack and then jump to that. We need to find some other function. So for example, if I disassemble system just to find the address of system, we could jump here. But for this challenge, they want us to return to a function called ret2win. So we want to change the return address to this function, and we can see here it does make a couple function calls. It calls print string. So if I grab this address, the string, and I know it's a string because put string prints, it takes one argument, which is a string or a character pointer, and it prints that to the terminal. And we see here the address of the string because it takes a pointer, and a pointer is just a memory address. And we see it's being stored in EDI. EDI is just a 32 version of the 64-bit register RDI. So we can see, well done, here's your flag being printed, and then we see something being passed to system. System takes a single pointer as an argument. Once again, a pointer is just a memory address. So if we print out this, it will execute the command bin cat with flag.txt. So this is the function we want to return to. We could just directly jump to one of these addresses, but let's jump directly to this address here. Alternatively, we could have done object dump tech-d, tech-m intel, because I like Intel syntax, and disassemble ret2win. We could look at that and less, and we can just look at the disassembly. And if I do slash to search and look for read, or actually, let me look for main. We see the main function, and we see the calls to put string and pwn.me, and we see the pwn.me function here with the same addresses. So you could just disassemble everything in object dumped. There's no reason to necessarily step through it in a debugger. I'm just more comfortable using a debugger. Alternatively, we can just do ret2win and then grep ret2win if we want to find this exact memory address. So let's open this up and let's start making our exploit. Vim exploit.py. Spelled that wrong. User bin and Python. We're going to use a module called pwn tools. So from pwn import all. We know we want our process to be ret2win, and we know we want to send 40 bytes of junk. So payload equals byte a times 40, and we can make comments here as well. So 40 bytes, 32 buff plus 8 for the base pointer. And now we want to add on the address of ret2win. I need to define that variable. So I'll do that up here. Variables, addresses, ret2win equals this hex address. Need to make it hex. And if I just do it like this, that's okay. Or actually, no, it's not, because this isn't a full 64-bit address, right? So I could grab this with all these zeros. Alternatively, I could just wrap it in P64 to make sure this is a 64-bit address. And now I need to send the payload to the process. So p.sendLine payload, make sure I spell it right, and p.receiveAll .decode, and let's actually print this out. Run our exploit and see what happens. So we get the same message from before, and then we see thank you, well done, here's your flag, but nothing is actually printed out. So what's going on? Let's go back to our exploit, open it up in Vim, Vim exploit.py, and instead of making, let's change this over here. I'm gonna comment this out, and instead of making this process, let's do gdb.attach, or debug, gdb.debug. So now look what happens when I run this program. It will automatically open this up in a GDB debugger, which is super cool. I think that's an awesome feature of using Pwn tools. So our program, it has automatically stopped. We see here that it's at _start. And if I want to continue, I need to hit C. But before I do that, let's set a breakpoint, break star ret2win. Actually, let's disable that breakpoint for now. Break pwn me. Continue. Our breakpoint has been hit. We see where we currently are on the stack. We're inside the very beginning of the pwn me function. We see the function prologue being about to be called, right? We see the base pointer being saved, and we see the local variables being created. So let's do ni, just a step one instruction. I'm just going to keep hitting ni. I'm going to keep doing this until we get to the read function. So we see everything being called with put string. Okay. Sorry if this looks pretty spammy, but here we go. Enter one more time. So the read function is about to be called. It's about to read our user input. In our case, it's about to read that payload that we sent. So look here, look at what's currently on the stack. It's a bunch of zeros. So there's really nothing on the stack. So if I hit enter one more time, now look, now the stack contains OX41, which is all of our A's that we sent. It's our 40 A's. And then we see here, the base pointer is being overwritten with A's. And then we see after the base pointer, we see the address of ret2win. And then we see the first address, which is the prologue, the epilogue, right? Push RBP. So this should be good. Let's hit ni, put string, okay, hit enter a few times. Here's the return address. Here's the program counter. We can see here, RIP, it will be calling pwn me. So hit enter. If I do a disassemble, we see we're inside the ret2win function. So we successfully did return-oriented programming. We changed the return address to be the address of the ret2win function. So if I do ni, we see put string is about to be called. Hit enter again. And we should see that message being printed to the screen somewhere. We should see you win being printed. getting a little lost in the sauce. Anyway, we do see the next call will be system, and we can see here RDI. So the argument being passed to system is bin cat flag.txt. We hit enter one more time, and it exits with a segfault. So I'm gonna hit Q to exit out of this. So why is that? Why isn't it not properly printing out our flag? Why is it going to the ret2win function, but it's failing once system is called? Now, if you're doing the 32-bit architecture version, you're not going to run into this issue. This is something pointed out in the beginner's guide. It's a quirk, it's a flaw with 64-bit architectures. So if we go to this beginner guide, underneath the common pitfall section, there is an entry for the move APS instruction, and there is an issue with it. So if you're segfaulting on this instruction, when you call buffered vprintf or system in x64, then ensure that the stack is 16 byte aligned before returning. So essentially, there's a weird quirk, a weird issue. The stacks need to be 16 byte aligned. And the way we're sending our exploit, our payload, we're violating that guarantee. We're violating that assurance. So in able to get the byte to be get the stack to be 16 byte aligned, we can do one of two things that are notated here. So it says we can try to pad our data with an extra return instruction before returning into a function, or we can just return further into the instruction. So there we have it. We have two options. We can either do a extra ret, an extra return instruction, or we can just jump deeper inside of the target function. I'll showcase both options here. So if I'm back in that original GDB window, so if I keep the return address here, I do need an address for a ret instruction. And I'm just going to grab the one already inside ret2win at address 400770. You could alternatively grab any one of these ret addresses that exist inside of the binary, but I'm just going to grab this one to make things simple. Okay, so if we're back inside of our exploit, we do need to modify this payload a little bit. So we're still going to keep the 40 bytes of junk to fill up our buffer, as well as the base pointer. But this time, instead of having the return address immediately point to the ret2win function, we're going to have it point to the address of the return instruction. So once again, I'm using the return instruction that is in the ret2win function, but alternatively, you could have used this one up above or any one that you're able to find within the binary. So come here, let's add another to our variables and addresses. Let's do ret equals p64, and let's slam in this address. And now let's do payload plus equals ret. Save and quit. Now let's rerun this. Well, actually, before we run it, we need to change. We don't want this to be GDB. We want it to grab the actual process on disk. So now when we run it, it prints out all this stuff. And then it says, thank you, well done, here's your flag. And it does print out flag. So it did successfully call the sys call, right? It successfully called system with our arguments of bin cat flag.txt. And this time the stack was properly 16 byte aligned. So a weird quirk, that's one way to do it. You can pad with an extra ROP, or you can return deeper into the function. So let's showcase that second way. I'm just going to copy exploit and make one called exploit2. Now let me open up exploit2. Our exploit2 will be the one we just did, and we'll call this one exploit. Let's modify this a little bit. So if we run this original one, we know it will not work. It tries, but it doesn't execute system because the stack is not properly 16 byte aligned. So this time, instead of jumping into ret2win directly, let's go into like an offset. Let's go deeper inside the function. You can probably use any one of these addresses, but I'm just going to grab this one. I'm going to grab the call or loading the argument bin cat, right? So if we look at this again, or it's right here. So if I grab this address that passes the string bin cat flag.txt into the register RDI, I'm just going to jump to this. So let's see if that works. Now let's save and exit. Now when I run it, I get the flag. So there you have it. There's two ways you can do it. The two different exploits that you can run. I'll just leave them on the screen just like this. So hopefully that made sense. Hopefully return-oriented programming isn't too crazy. It isn't too scary. It's not too different than other buffer overflow attacks. Once again, you'd really only need return-oriented programming when something, when something like NX is enabled, when the stack is not marked as executable. And if you don't have checksec, instead we could have come here and we can do something like VM map, the virtual memory mappings. And if we look at the stack here, we see it has two permissions, read and write, but it does not have the executable bit enabled. So that's really it for this video, guys. Hopefully you enjoyed it. Hopefully you learned something new. There is a difference between binary execution and binary exploitation on a 32-bit architecture that has a different stack frame than something on a 64-bit architecture that has a different stack frame, right? So as always, let me know in the comments down below if you found a different way to solve this or a better way. As always, take it easy and see you guys in the next video.